Okay, this is our last section on Taylor and Maclaurin polynomials, our series unit, functions as series. And so this is writing Taylor and Maclaurin series. We've looked at a couple different ways that we can come up with sort of the general form of a power series. And this is really going to show you the form that pretty much all convergent power series are going to take. Not all power series are going to converge, but the ones that do are going to be Taylor or Maclaurin series, okay? So this theorem here says that if f is represented by a power series, so we're using some series to stand for f of x, for all x in some open interval, then the coefficients are going to follow that Taylor series pattern, and the value of f of x is going to be equal to the sum of that infinite series, okay? Now, this little remark to the side here is really important. What we want to make sure that we understand is that this says, if a power series converges to f of x, then the series must be a Taylor series. It does not say that every Taylor series converges. So it's kind of like the whole all squares are rectangles, but not all rectangles are squares kind of thing. So if a power series converges to a function f of x, it must be a Taylor series. But not all Taylor series are going to converge to a function. The ones that do are definitely going to have to be Taylor series, okay? So here is the definition of a Taylor and Maclaurin series, which is really just what we already know about Taylor and Maclaurin polynomials. We're just extending this to be an infinite series. So we have our general term, and this goes on forever. Now, we're going to be using the pattern that we see from the different terms of the Taylor polynomial to help us extend to find the corresponding power series. So for example here, what we've got written out is the fourth degree Taylor polynomial for the natural log of x centered at 1. And so if you look at the pattern, okay, we see that it's alternating. We see the what the fractions are doing. It's 1 over 1, 1 over 2, 1 over 3, and so on and so on and so on. And so what we can look at here is we can use that pattern to now set up a series in this term. Now, we are not going off of the term numbers as they were in the original polynomial. This is now our new series. This is term 1, this is term 2, and ... this is term n, okay? So we need the first term to be positive. So if n is equal to 1, that's why we want the exponent here to be n plus 1 for the negative. Because if it was just negative 1 to the n, when n is equal to 1, this term should be negative. But since we need it to be positive, we need to increase the value of n. That's how we're going to get the signs, okay? Notice that that's not the same as how it worked up here. That was n to the 0, n to the first, and so on and so on and so on. So this one would have just been negative 1 to the n is how that would work out. So we're looking at a new series when we start putting this together, and that's something that we're going to pay attention to on these examples, okay? So let's look at this first example here to kind of get us started. So we want to use the function f of x equals the sine of x to form its Maclaurin series and determine the interval of convergence. I'm going to try to give myself a little bit of room here. Okay, so they've given us the pattern there for the Maclaurin series to reference if we need to. So the first thing we need to do is start building out the first few terms of our series and then use that to be able to find the pattern. So we need to start by finding all of these successive derivatives of sine of x at the center, which is 0. So there's our list of derivatives up to the first 4. After that, this is going to be a cycle. So this is just going to repeat over and over again. So we can use those coefficients and use the pattern that we know for Maclaurin series. And we're going to set this up. So we're going to say that f of x, which is the function sine of x in this case, is going to be equal to f of 0, so that's 0, plus f prime of 0 times x, so that's going to be plus 1x. And then the next one is going to be f double prime of 0, so that's going to be 0x squared over 2 factorial. Then we get minus 1x cubed over 3 factorial plus 0x to the 4th over 4 factorial. And I'm going to go just one more. We would get plus, this one would be positive 1x to the 5th over 5 factorial plus dot, dot, dot. Okay. Now, first thing I noticed right away is that every other term doesn't really exist because it's just 0. So we don't need to write it out. So this term we can eliminate, this one we can eliminate, this one we can eliminate, the 6th one we could eliminate. So we're going to write a new series without all those zeros in it. So now we have x, the next one is minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial. The next one, if we were to extend the pattern, would be minus x to the 7 over 7 factorial plus dot, dot, dot. Now, we need to figure out the general term in this series. But notice, this is a new series. We are now looking at, this is the term where n is equal to 0. This is the term where n equals 1, n equals 2, n equals 3. So it's not going to be as simple as just following the pattern from the original Maclaurin series, okay? We're trying to build this new power series for sine of x based only on the terms that exist. Okay, there was one like this in the homework last week. So now, when we want the general nth term, we need to base this on the pattern that we've got here. So the first thing I see is that it is alternating, okay? So I know that I've got to have negative 1 to some power. Now, I need to make sure that it's either going to be n or n plus 1, depending on what we need. So let's try it with just n. Negative 1 to the 0 would be positive 1, so that would make the first term positive. Negative 1 to the first would make the next term negative. That's correct. And then if it was second, that would make the next term positive. That's correct. So it looks like that's going to be right. Okay. Now, I noticed that the powers are all odd numbers. So hopefully you recognize the pattern for odd and even numbers. Even numbers are 2n, odd numbers are 2n plus 1. So the power here is going to be x to the 2n plus 1 power. That's how we get odd numbers. So let's double check. If I do 2 times 0 plus 1, that means I get x to the first. That's good. If I do 2 times 1 plus 1, we get 3. 2 times 2 plus 1, we get 5, and so on. So that's good. And then I want those same numbers factorial in the denominator. So this is going to be 2n plus 1 factorial plus dot, dot, dot. So that is our Taylor series. Now we could leave it written like that, or we could come down here and write it as a sum from n equals 0 to infinity of our general term, negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. So that is how we get our series, okay? The idea that we're kind of shifting the terms, whereas originally this was the 0 term, 1 term, 2 term, 3 term, and so on. We've kind of transformed it a little bit when we got rid of those 0 terms, and so we wanted to write a series that is only going to generate non-zero terms. That's always what we're looking for. So that's why this process is changing just slightly, okay? Now, it wanted us to find the interval of convergence, and to do that, we need to use the ratio test. So we want to look at the limit as n approaches infinity of the absolute value of, we need this all the n plus 1th term. So we have negative 1 to the n plus 1 times x to the 2 times n plus 1 over 2 times n plus 1 factorial, and then we're going to multiply that by the reciprocal because we're dividing. So this will be 2n plus 1 factorial over negative 1 to the n, x to the 2n plus 1s. Now, because of the absolute value, we can ignore the negatives altogether. That's just fine. And we can clean this up just a little bit by multiplying out where we need to. So now I have x to the, that's going to be 2n plus 2, so this will be 2n plus 3, which means this is over 2n plus 3 factorial times 2n plus 1 factorial over x to the 2n plus 1. Okay, this is getting a little squished. I hate to do it this way, but I'm going to work backwards here now. So when we do that, when we subtract exponents here, 2n plus 3 divided by x to the 2n plus 1, and we subtract, we're just going to get x squared. And it'll be in the numerator. So we have the limit as n approaches infinity of, we have x squared. And then it's going to be over 2n plus 3 times 2n plus 2, and then 2n plus 1 on down is going to cancel out with the 2n plus 1 factorial that we had. So this is what we had left. And according to the ratio test, in order for this to converge, we need this to be less than 1. Now, we only want the limit as n approaches infinity, so we can bring out the absolute value of x squared times our limit, which is going to come out to 0. So what we end up with is the statement that 0 is less than 1, which is always true. So that means that this series is going to converge for all x. Its radius of convergence would be infinity. So that means that this series is always going to give you the value of sine of x if you add up this infinite series. So that's kind of neat. Now, again, looking at what we know with Lagrange error, you can determine how accurate the number of terms is that you would need. The infinite series is going to perfectly give you the value of sine of x. It is equal to sine of x. If you cut down to a finite number of terms, that's going to approximate it. And that is what like your graphing calculators do when they want to determine the sine of 17. It doesn't have that stored. It's using the minimal approximation that it needs to in order to be able to show you a correct 10 digits on your calculator screen. So that's kind of interesting. So that's where we're going to stop for this first example. The next one, if you look, example 2 says show that the Maclaurin series for sine of x converges for all x, which is literally what we just did. That's what we come up to. So we're going to skip that example, and I will pick up with some more examples in the following videos.